This is USACO 2019 January Contest Gold, Problem 2, Sleepy Cow Sorting. And in this problem, Farmer John is attempting to sort his N cows, conveniently numbered 1 to N, before they head out to the pastures for breakfast. Currently, the cows are standing in a line in the order permutation 1 to permutation N, and Farmer John is standing in front of cow P1. He wants to reorder the cows so that they are in the order 1 to N, with cow 1 standing next to Farmer John. Today the cows are a bit sleepy, so at any point in time, the only cow who is paying attention to Farmer John's instructions is the cow directly facing Farmer John. In one time step, he can instruct his cow to move k paces down the line for any k between 1 and n minus 1 inclusive. The k cows whom she passes will amble forward, making room for her to insert herself in the line after them. For example, suppose that n equals 4 and the cows start off in the following order: 4, 3, 2, and 1. The only cow paying attention to Farmer John is cow number 4. If he instructs her to move 2 paces down the line, the order will subsequently look like this. Now the only cow paying attention to Farmer John is cow number 3, so in the second time step, he may give cow 3 an instruction and so forth until the cows are sorted. Farmer John is eager to complete the sorting so he can get back to farmhouse for his own breakfast. Help him find a sequence of instructions that sort the cows in a minimum number of time steps. Okay, first we'll need to read the input, which is this. The first line of input contains n, which is the number of cows, and then the permutation of cows. And that's pretty simple, it's straightforward. So we'll move on to the output, which will first output a single integer of the minimum number of steps required to sort the cows, then each individual instructions that Farmer John will give to the cow at the front in order to sort the cows. And before we get into this problem, we need to note a few observations. The first observation is that the answer can be found by the number of cows. Before we get into this, we can split the original permutation of cows into two parts. The second part, the maximum number of cows from the back, which is sorted. In this case, in this sample case that I made, it would be 3, 4, 6, and 7, and the which we'll call the suffix. And the parts preceding this part, in other words, that were not included in the sorted thing, we'll call the prefix. And we can note that the answer will always be the length of the prefix, since the suffix is already sorted. All we need to do is take from the first part and arrange these into, or insert these into the suffix in order to completely sort the cows. And now that we've got the answer, we need to get the actual instructions, and then we can do this with our second observation, that the number of times each cow in the prefix will need to move backwards is, first, the number of cows remaining in the prefix minus 1 plus the position in the sorted array. So in first, moving number 1, there's three cows in the unsorted prefix, so that's 3 minus 1, which is 2, plus, and it's at the first index of the sorted array, so it would be plus 0, which would be two spots back. Next, 2. We're moving cow number 2 back, and there's 2 cows in the prefix, so that's 2 minus 1, and it's at the second index of the sorted array, plus 1, so that's 2 paces back. And then number 5, there's one cow in the prefix, so that's 1 minus 1 plus, it's at the 5th index of the sorted array, so plus 4, that's 4. And then we'll move number 5 4 paces back, and then the cows are sorted. Now that we've got this information, we can get to programming. I have the basics of the program set up, like input reading and output setting. So let's get right into it. First, we'll need to read n, which will make a static variable so we can access it everywhere, as well as create an array of the original spots of the cows. First read n, and then read the positions of the cows. This should be enough for the input reading, actually. It's a very simple input. Now let's get to programming. Actually, since separating the prefix from the suffix is such a simple process, we'll include it in the initialization function. We'll put sep for separator. Also, it'll just be easier to read if we made this start from 1 and not set the indexes start from 1 and not 0. So we'll set sep to n while original of sep, or sep minus 1 is greater than or is less than original of sep minus minus. And then separate down one more time. And this will get our answer already, actually. So we'll start by printing out our answer. We'll set it to system.out.println so we can debug the answer in case anything goes wrong. And we'll test out our code so far, and it prints out 3 like it should. At this point, it's important to discuss what data structure we'll use to calculate the instructions. And you might think, since the suffix has to remain sorted, we'll use like tree set or array list, but it's simply too slow. And the functionalities we need of this data type is getting the number of values that are less than a value inside the data structure, as well as update the data structure as we need. And the perfect one for this is binary index tree, or one might call it, or others call it, a Fenwick tree. And to implement this, we'll first create D. Actually, we'll just call it binary index tree to make it a lot more intuitive. and we'll initialize the array. I'm assuming everyone watching already knows what binary index trees are, but if you don't, there are plenty of great resources online that explain exactly what a binary index tree is, what it does, how to initialize it, so I won't go through it in this video. We'll do static void update and x at index x, and normally you would put another variable to signify how much it's going up or down by, right? But it's not necessary here because we'll always be only updating it by +1. So for int I is equal to x, I is less than or equal to n, I plus equals I at I don't know how to pronounce that, but that is just how you implement it. And we'll update the binary index tree, and then we'll also implement the get x int total equals 0, for int I equals x, I is greater than 0, I is minus equals I at not negative I, total plus equals to binary index tree I, and return total. And how we're going to use binary index tree to implement this is that we will set the value of an index to be true or to be 1 if the element in question is in the suffix. In other words, if it's in the sorted part of the cows, it will be set as 1, and otherwise it will be 0. That means that if we just get the sum or the prefix sum of the values from 0 to the index, we can get how many cows should be in front of the cow in the sorted array, or in the suffix. It's a bit hard to explain, but it's easier to get if you just look at the code. And we'll iterate through 0 to less than sep I plus plus, until it's equal to sep, I think. And then what we'll do is we'll use a string builder to build our answer, since it might time out if we just print onto the console. sp.append get for here I forgot to do original of sep, not sep, and we'll get original I and then we'll first get sep minus I plus get. then append space, and then we'll update it so that can update the suffix, and then we'll print out our answer, and make sure to get rid of the white space at the end or it'll cause problems. We'll try this and see if it works. 223 seems like it's working, so we'll set this to out.println and we'll test out our code. We will submit the code and just wait for it to grade. And it seems like we got everything. That's all.